Imagine standing at the base of a towering mountain range, its peaks piercing the sky, and feeling that profound sense of awe that only nature's grandest creations can inspire. But what if I told you that these silent, majestic giants are far more than just rock and ice? They are keepers of secrets, ancient, sprawling libraries written in stone, holding stories far older than humanity itself. Deep within the Earth's crust, hidden faults and fractures act as geological archives, preserving clues from a past so distant and turbulent it challenges our very understanding of time. These fractures are not just cracks in the ground, they are portals that allow us to travel back millions, even billions, of years to witness continental collisions, climate revolutions, and the very forces that gave shape to our world. In this video, we're going to embark on a journey to crack open the mountains not with picks and shovels, but with curiosity and science. We'll explore how these deep faults reveal astonishing details about epic continental shifts, prehistoric climates that saw jungles turn to deserts and oceans freeze over, and even the faint, fossilized traces of early life. From the colossal tectonic collisions that thrust entire mountain ranges toward the sky to the subtle, almost imperceptible tremors that hint at changes yet to come, we'll uncover how geologists read these natural vaults to decode Earth's deepest enigmas. You'll see how mountains become storytellers, narrators of a hidden history written in layers of rock, mineral deposits, and seismic whispers. And this isn't just about satisfying scientific curiosity. Understanding these forces is crucial to predicting our planet's future, how it might respond to changes, where resources lie hidden, and how we can better prepare for natural events that ripple through human lives. So get ready to see the world beneath your feet in a completely new light. This is a journey into the heart of our planet's mysteries, and by the end, you won't just look at a mountain, you'll listen to it. Think of Earth's surface not as something fixed and permanent, but as a collection of enormous, slow-moving plates floating on a layer of hot, malleable rock below. When two of these continental plates meet, they don't just stop, they collide with a force so immense it can only be measured on a geological timescale. This is the engine of mountain building. In some places, like where the Indian plate smashes into the Eurasian plate, the crust crumples and folds, being pushed upward to form the breathtaking peaks of the Himalayas. In other regions, such as along the west coast of South America, one plate is forced beneath another in a process called subduction, melting rock and fueling volcanoes that build up the Andes. These aren't quick events, they are epic sagas unfolding over tens of millions of years, where rock behaves like putty under extreme pressure, slowly deforming and stacking upon itself. The incredible stress generated by these collisions doesn't just push rock upward, it also causes it to crack and break under the strain, creating those deep faults that slice through the crust. These fractures are like the seams of a giant, unfinished sculpture, and they give geologists a direct line of sight into the interior of the mountain, exposing layers that would otherwise remain hidden miles below the surface. By carefully reading the sequence of these layers, where ancient sedimentary rocks might be found perched high above younger granite, scientists can essentially rewind the tape, reconstructing the precise order of events that created the landscape we see today. They can find evidence of ancient rivers that once deposited sediment, of seas that long ago vanished, and even fossilized clues to life that thrived in environments completely transformed by these titanic forces. So when you look at a mountain range, you're not just looking at a beautiful view, you are looking at the direct and dramatic result of our planet's restless, dynamic nature, a frozen moment in an ongoing story of collision and creation. But just as a detective must understand the different types of evidence at a crime scene, a geologist must learn to read the distinct signatures left by various fault types. The Earth's crust doesn't just crack randomly. It fractures in predictable ways depending on the immense forces acting upon it, and each type of break tells a completely different story about our planet's past. First, consider the thrust fault. Picture two massive blocks of rock being squeezed together by unimaginable pressure, like a rug being pushed across a floor until it buckles and folds. In a thrust fault, one block is forced up and over the top of another, often for many miles. This incredible action can plow ancient, deeply buried rock layers and shove them right on top of much younger sediments. It's as if someone took a chapter from the very beginning of Earth's history and slammed it down on a page written only recently. These faults create natural windows, allowing scientists to study environments and climates from hundreds of millions of years ago without having to drill miles into the crust. The famous Lewis Thrust in Glacier National Park is a perfect example, where billion-year-old Precambrian rock rests peacefully atop much younger Cretaceous sandstone, a silent testament to a colossal collision that shaped the North American continent. Then there are the strike-slip faults, where the movement is primarily horizontal. Here, the ground doesn't move up or down so much as it grinds sideways, as if two giant hands are sliding past each other. The most famous of these is California's San Andreas Fault, a stark line on the landscape where the Pacific Plate is steadily sliding northwest relative to the North American Plate. This lateral motion is a clear signal of transform plate boundaries, where two tectonic plates are scraping past one another. The relentless grinding along these faults pulverizes rock into a fine, powdery substance called fault gouge, and often polishes the fault surfaces into a glossy, grooved finish known as slickensides. By studying the direction of these grooves, geologists can determine the exact path the rocks traveled, reconstructing the intricate dance of the plates over millennia. In stark contrast to the compression of thrust faults, normal faults are born from extension, from the Earth's crust being pulled apart. Imagine stretching a piece of taffy until it finally thins and snaps. That's the process at work in places like the Basin and Range Province in Nevada and Utah, or the Great East African Rift Valley, where the continent is slowly being torn in two. A normal fault occurs when one block of rock drops down relative to another, creating a steep scarp. This stretching and thinning of the crust provides vital clues about continental breakup, the very initial stages of how a supercontinent like Pangaea began to fragment and give birth to new ocean basins. By mapping these faults, scientists can measure how much a region has stretched and even begin to predict its future geological evolution. Each of these fault types leaves behind a unique set of clues for the geological detective. Beyond the slickensides and gouge, mineral deposits can crystallize from fluids circulating through the fractures, sealing in chemical information about the temperature and pressure conditions at the time of the earthquake. By meticulously analyzing these diagnostic features, geologists can do more than just identify the type of fault. They can reconstruct the entire stress field, the direction and magnitude of the immense forces that warped the landscape. It's this detailed forensic analysis that allows us to transform a simple crack in the rock into a vivid, dynamic picture of the tectonic dramas that have endlessly sculpted our world. Now, with a clear picture of how different faults form and what they can tell us about the forces that shaped them, we face the next great challenge: figuring out exactly when all this happened. A fault might show us the direction a block of rock moved, but without a timestamp, that event remains floating in a vast sea of geological time. This is where one of the most powerful tools in all of science comes into play: a technique that lets us read the atomic clocks trapped inside the rocks themselves. Radiometric dating allows geologists to assign absolute ages to the cataclysmic events recorded in these deep faults, transforming a relative sequence of events into a precise and detailed timeline of our planet's history. The entire principle is built upon a simple yet profound natural phenomenon: radioactive decay. Certain elements like uranium or potassium are unstable. Their atoms spontaneously break down over time at a rate that is absolutely constant and predictable, transforming into different, more stable elements like lead or argon. This isn't a process that can be sped up by heat or slowed down by pressure. It is an unwavering atomic metronome, ticking away with perfect regularity for billions of years. When a mineral like zircon crystallizes from a magma deep underground, it acts like a brand new stopwatch. At the moment it forms, it locks certain radioactive isotopes, known as parent isotopes, into its crystal structure. From that instant, the clock starts. As the eons pass, the parent isotopes decay into their daughter products. By very carefully measuring the ratio of remaining parent isotopes to accumulated daughter isotopes in that mineral today, scientists can calculate exactly how long that clock has been running. It's a direct measurement of time since the mineral formed. Different clocks are used for different time scales, each with its own strengths. For the most ancient events, like the initial formation of a continent or a collision that happened over 1 billion years ago, the uranium lead dating method is the gold standard. Zircon crystals are incredibly durable and resistant to resetting, making them perfect time capsules. By dating zircons found in rocks that were heated and deformed during a major faulting event, researchers can pinpoint the age of that mountain-building episode with astonishing precision, sometimes down to a few million years on events that are billions of years old. For more recent geological activity within the last 100,000 to a few million years, the potassium-argon method becomes incredibly valuable. This is especially useful for dating volcanic ash layers that are often interwoven with faulted sedimentary rocks, providing a clear age bracket for when the fault must have moved. The real power of this technique in fault studies comes from understanding how these clocks can be reset. The immense heat and pressure generated along a fault during a major earthquake can be enough to essentially reboot the atomic stopwatch in certain minerals. It's as if the tremor jolts the clock, zeroing out the daughter products and allowing a new timing sequence to begin. So, a mineral might originally be 1 billion years old, but if it was caught in a fault zone 200 million years ago, the radiometric date will reveal that younger, reset age, the age of the tectonic event itself. By collecting samples from various points along a major fault system and dating the minerals within them, geologists can begin to stitch together a history not of a single earthquake, but of entire periods of tectonic unrest. They can identify distinct pulses of mountain building, known as orogenies, and correlate these events across vast distances. This is how we know, for example, that the Appalachian Mountains in the eastern United States and the Caledonian Mountains in Scotland and Norway are actually fragments of the same ancient mountain range, torn apart by the opening of the Atlantic Ocean, because their fault systems record identical ages of formation. This chronological framework is what allows us to move from simply reading the story in the rocks to placing that story on a calendar, connecting the rise and fall of entire mountain ranges to the grand, global cycle of supercontinents assembling and breaking apart. So, with the ability to precisely date when these ancient mountains formed and their faults shifted, we unlock a second, equally astonishing capability, using those same cracks in the crust as windows to peer into the very climate of the past. It's a remarkable transformation of perspective. Where we once saw just rock and fracture, We can now see ancient rainforests, vast deserts, and frozen tundras, all preserved in the pages of a stone ledger opened by tectonic forces. Deep faults do more than just move blocks of the earth. They act as elevators, lifting entire packages of sedimentary rock that were once buried in the deep, dark quiet of the subsurface, and delivering them to the surface where sunlight and science can reveal their secrets. These uplifted layers are time capsules, and within them we find the diaries of past environments, written in a language of fossils, minerals, and atomic isotopes. Take, for instance, a drive through the rolling folds of the Appalachian Mountains. The rocks exposed along the highway cuts tell a story that seems almost impossible to believe today. Within those layers, geologists find vast, thick seams of coal. But coal isn't just a rock, it's condensed plant matter, the compressed remains of an unimaginably vast and dense forest. These coal seams are the direct evidence of the Carboniferous period, a time over 300 million years ago when the atmosphere was thick with oxygen and the land was covered in sprawling, swampy jungles of giant ferns and primitive trees. The very existence of that coal, now lifted high into the mountains by ancient faults, tells us that this region once basked in a hot, wet climate with torrential rainfall, a world teeming with life that would eventually fuel the Industrial Revolution. It's a stark contrast to the temperate forests that cover the Appalachians today. Conversely, in other parts of the world, faults expose layers of rock filled with evaporites, minerals like gypsum and halite that form when bodies of salt water evaporate completely under a scorching sun. Finding a band of these crystals within a mountain range is like finding a desert buried in the sky, a clear signal that the area was once a parched, arid landscape, perhaps similar to the modern Dead Sea. But the most precise climate data doesn't always come from something you can see with the naked eye. Sometimes it's written in the invisible chemistry of the rock itself. This is where isotopic analysis becomes our most powerful time machine. Elements like oxygen and carbon have different isotopes, which are essentially atoms with slightly different weights. The ratio of these isotopes in a mineral is exquisitely sensitive to the environmental conditions when that mineral formed. A tiny fossil shell made of calcium carbonate and pulled from a sedimentary layer exposed by a fault holds a record of the ocean temperature in which the creature lived. By measuring the ratio of oxygen isotopes in that shell, scientists can calculate the water temperature with surprising accuracy, determining whether that ancient sea was warm and tropical or cold and polar. Similarly, carbon isotopes locked within ancient soil layers or marine sediments can reveal massive shifts in Earth's carbon cycle. A sudden change in the ratio can indicate a dramatic event, like the volcanic outbursts that triggered past greenhouse extinctions or the explosion of plant life that sucked carbon dioxide out of the atmosphere and led to an ice age. These chemical fingerprints allow researchers to track the pulse of the planet's climate system over millions of years, seeing the cycles of ice ages and warm periods, and understanding the fundamental drivers behind them, from the wobble of Earth's orbit to the eruption of supervolcanoes. This incredible archive, preserved and presented by the action of faults, gives us a long-term perspective on climate change that is absolutely vital. It shows us that Earth's climate has never been static. It is a dynamic system that has swung between extremes, but more importantly, it provides the baseline data against which we can measure the unprecedented speed and magnitude of the changes happening today. By studying how climate responded to natural drivers in the past, we can refine our models for the future. This intersection of geology and climatology turns mountains into more than just beautiful landscapes. They become the planet's librarians, carefully storing the records of ancient atmospheres and offering us the profound lessons contained within. But the story of life preserved in rock isn't just about bones and shells. It's also written in the most delicate of details, often saved from decay by the very chemistry of the fault zone itself. Fluids circulating through these deep fractures can be rich in minerals like silica or calcium carbonate. When these mineral-laden waters encounter the remains of a creature, something magical can happen. Instead of the organism simply rotting away, the minerals can rapidly precipitate, encasing even the most fragile soft tissues, the delicate wings of an insect, the fine veins of a leaf, or the intricate gill structures of an ancient shrimp in a protective stone cast. This process, known as permineralization, creates fossils of such stunning detail that they offer a window into the anatomy and ecology of creatures that lived hundreds of millions of years ago. While the world-famous Burgess Shale, with its exquisite soft-bodied fossils, is not a direct product of faulting, it exemplifies this principle of exceptional preservation through rapid burial and mineralization, a process that faults are uniquely positioned to facilitate. The constant fluid flow and the creation of protected pockets within a fault system make them natural factories for these kinds of priceless preservation events. This allows paleontologists to study not just the skeletons of ancient life, but the complete organisms, providing irreplaceable clues about their behavior, their diets, and their place in the long-vanished ecosystem. It transforms a simple fossil from a static rock into a dynamic snapshot of a living, breathing moment from an unimaginably distant past. By meticulously mapping these biological treasures against the tectonic timeline provided by the faults that expose them, scientists can draw powerful connections between the physical reshaping of our planet and the evolution of life upon it. The rise of a new mountain range does more than just create breathtaking scenery. It fundamentally alters the world. It can block prevailing winds, creating a rain shadow that turns a lush region into a desert on one side and a swamp on the other. It can separate populations of animals, leading them down independent evolutionary paths until they become entirely new species. It can create new coastlines, new river systems, and entirely new habitats for life to explore and adapt to. The fossil record preserved in these fault zones often captures these pivotal moments. We can see the explosion of new mammalian species in the rocks just after the asteroid impact that ended the age of dinosaurs, an event likely linked to the massive tectonic upheavals it triggered globally. We can trace how the uplift of the Isthmus of Panama connected North and South America, allowing a great American biotic interchange where species like armadillos moved north and cats moved south, forever changing both continents. This is the grand synthesis where geology and biology merge into a single story. The faults provide the stage and the timeline, and the fossils provide the actors and the plot. It's a powerful reminder that the ground beneath our feet is not a passive platform for life, but an active participant in its grand billion-year narrative. The very forces that fracture continents are the same ones that, indirectly, help write the evolutionary playbook for every living thing on Earth. And this incredible interplay between deep geological processes and the fossilized remains of ancient life leads us directly to another profound connection, one that has fueled empires, built economies, and literally shaped human civilization: the vast mineral wealth that is so often concentrated in these very same fault zones. It turns out that the fractures which archive Earth's history are also the very same plumbing systems that transport and trap the resources we depend on. When those titanic plates collide and the crust shatters, it doesn't just create a static crack. It opens up a superhighway for superheated water. Miles below the surface, water circulates and gets heated by the Earth's internal warmth, becoming a powerful hydrothermal fluid. This fluid acts as a universal solvent, leaching out valuable metals like gold, silver, copper, and zinc from the surrounding rock as it courses through the network of faults. But the real magic happens when these metal-rich fluids encounter a change in their environment. If the pressure suddenly drops, the fluid can flash into steam, much like water boiling in a kettle. This rapid boiling causes the dissolved minerals to instantly precipitate out of solution, effectively plating the walls of the fault with veins of pure metal. Alternatively, the hot fluid might encounter a chemical change, a reaction with a different type of rock, that forces it to drop its precious metallic cargo. Over millions of years, this slow, persistent process can transform a simple fracture into an economic bonanza. There is no better example of this than the legendary Mother Lode system that runs through the heart of California's Sierra Nevada. This isn't a single vein of gold, but an entire series of parallel fault zones that acted as the perfect conduits for gold-rich hydrothermal fluids. These fluids, generated during the plutonic events that built the mountains, migrated upward and then boiled and cooled within these faults, depositing their glittering treasure. It was the erosion of these very mountains that then washed the gold into riverbeds, creating the placer deposits that sparked the 1849 gold rush and drew hundreds of thousands of prospectors to change the course of American history. But the story doesn't end there. Modern mining continues to target the primary source, the hard rock veins deep within the fault zones themselves, proving that the geological lottery ticket created millions of years ago is still paying out today. The economic story of faults extends far beyond glittering metals, deep into the very energy that powers our modern world. The same tectonic forces that create thrust faults and folds are master architects of structural traps for hydrocarbons. Picture a layer of porous sandstone, saturated with ancient organic material that has cooked over time into oil and gas. Now imagine a fault moving a dense, impermeable layer of shale right on top of that reservoir, or a fold arching the rock into a giant dome. The fault, or the crest of the fold, acts as a seal, an enormous natural cap that prevents the buoyant oil and gas from continuing their slow migration toward the surface. They become trapped, pooled, and waiting, sometimes in colossal quantities. This is why understanding the precise geometry of fault systems from seismic data is the first and most critical step in energy exploration. Geologists aren't just looking for oil, they're looking for the specific rock structures that faults have created to hold that oil prisoner. This knowledge dramatically reduces the multi-million-dollar risk of drilling a dry hole, turning geological insight into one of the most valuable commodities of all. So the next time you hold a gold coin or fill your car with gasoline, consider the incredible journey those resources took. They are not just products of our industrial age. They are the direct legacy of earthquakes that shook the world long before humans walked it, of mountains that rose and fell over epochs, and of the patient, hidden circulation of fluids through deep planetary scars. The practical application of deciphering these mountain structures is a powerful reminder that the Earth's hidden past is not an abstract academic pursuit. It is a tangible, foundational part of our present reality, underpinning the technologies we use and the societies we've built. And this incredible interplay between deep geological processes and the concentration of mineral wealth leads us to an even broader realization. The story of faults is the story of the very landscapes we inhabit. The initial, dramatic collision of plates might thrust rocks skyward to form a mountain range, but that's only the opening act. For millions of years afterward, the ongoing, often subtle movement along deep faults acts like a master sculptor, patiently chiseling and shaping the world around us into the valleys, ridges, and basins we recognize today. This isn't a static process, it's a dynamic, eons-long conversation between the powerful uplift from below and the relentless forces of erosion from above. The result is a living topography that directly dictates where water flows, where life thrives, and ultimately, where humans choose to build their homes and cities. Perhaps the most stunning textbook example of this is the vast and awe-inspiring Basin and Range Province, which stretches across Nevada, Utah, and into neighboring states. From the air, this region looks like a giant has dragged a comb across the earth, creating a series of parallel, north-south trending mountain ranges separated by flat, expansive valleys. This distinctive pattern is the direct handiwork of normal faulting. As the crust in this region was stretched and pulled apart over the last 30 million years, it fractured along these deep faults. Huge blocks of crust, tens of miles long, dropped down along these fractures to form the valleys, known as basins, while the adjacent blocks remained standing as the mountain ranges. This geological domino effect created a landscape of dramatic contrasts. The towering ranges, catching moisture from the atmosphere, become biological islands, forests of pine and aspen, thriving at higher elevations, home to unique species isolated from other mountain islands by seas of desert below. The basins, meanwhile, are often arid, collecting the sediment that erosion washes down from the peaks. They become internal drainage systems, where rivers flow inward to form ephemeral lakes or simply sink into the dry earth. This fault-controlled geography is the ultimate arbiter of life here, determining which areas will be lush with vegetation and which will be starkly beautiful deserts. But the work of the fault doesn't stop at creating the initial block. It sets the stage for the next artist, erosion. Once a block is uplifted, even by a tiny amount each year, it immediately becomes a target for wind, water, and ice. Rivers, following the path of least resistance, often seek out the weakened rock along the fault lines themselves, carving deep, dramatic canyons that expose the very heart of the mountain. The Grand Canyon, while not solely the product of a single fault, is a monumental example of how water can exploit tectonic weaknesses to reveal a billion years of geological history. Every grain of sand and silt that the river carries away from the mountain is transported downstream, eventually being deposited in the low-lying basins or on coastal plains. This sediment, the literal dust of mountains, becomes the fertile soil that supports agriculture downstream or piles up into thick layers that will one day, through renewed tectonic action, be compressed into the sedimentary rock of the future. It's a perfect planet-scale recycling system. The fault builds up the raw material, and erosion tears it down to build something new elsewhere. This endless interplay between construction and destruction doesn't just make for pretty scenery, it fundamentally shapes human history. Ancient civilizations didn't settle randomly. They flourished in river valleys like the Nile, the Indus, or the Tigris and Euphrates because those rivers flowed through basins created by tectonic forces, depositing the rich, life-giving soil that made agriculture possible. The very fertility that gave rise to these cradles of civilization was a gift from the slow, grinding work of faults and the erosion they facilitated. The location of a mountain pass that became a critical trade route, the presence of a natural harbor protected by a rocky headland, the course of a mighty river, all of these are often dictated by the underlying geological structure, a structure carved by deep faults over millions of years. When we recognize these profound connections, we begin to see the landscape not as a static backdrop to human drama, but as an active, shaping character in our story. The ground beneath our feet has been directing the flow of water, life, and human ambition for millennia, and it all started with a crack in the Earth's crust. Yet for all their power to shape the landscape over millennia, these deep faults also hold the potential for sudden, catastrophic release, the earthquake. It's a humbling reminder that the same forces which patiently built the mountains over millions of years can undo their work in mere minutes. Every tremor, from the barely perceptible to the devastatingly powerful, originates along these fractures in the Earth's crust. But rather than just being sources of destruction, these seismic events are also vital sources of information. By learning to read the history of past quakes preserved in the rock record, scientists are transforming our ability to understand, anticipate, and ultimately live with the immense power of our dynamic planet. This detective work has its own specialized field, Paleoseismology. Imagine a team of researchers carefully digging a deep, narrow trench straight across the trace of an active fault, like the San Andreas in California. They're not looking for oil or water, they're excavating a cross-section of recent geological history. As they clean the vertical walls of the trench, a story written in soil and sediment is revealed. They might see a distinct layer of ancient peat from a long-vanished swamp, now abruptly severed and offset by several feet. Above it, a different layer of stream gravel shows the same sudden jump. Each of these offsets is the silent signature of a major earthquake that ruptured the surface centuries ago. In other trenches, they might find evidence of sand volcanoes, small cones of fine sand that were forced upward through overlying clay by the intense shaking of a quake, a process called liquefaction. Or they might uncover chaotic piles of rock and soil, known as colluvial wedges, that tumbled down a freshly created fault scarp shortly after a quake and were then buried by subsequent peaceful sedimentation. By carbon dating bits of charcoal or plant material found just above and below these earthquake horizons, paleoseismologists can assign precise dates to these ancient cataclysms. This allows them to build a timeline of past seismic activity, calculating the average time between major events, the recurrence interval, and estimating how powerful each one must have been. Perhaps the most startling and ultimately life-saving application of this technique has been along the Pacific Northwest coast. For a long time, this region was thought to be relatively quiet seismically. But paleoseismological studies, combining evidence from offshore sediment cores and onshore coastal marshes, revealed a terrifying truth. The Cascadia subduction zone, where the Juan de Fuca plate is sliding beneath North America, has a history of generating colossal megathrust earthquakes on par with the 2004 Sumatra quake. The evidence was in the land itself. Entire stretches of coastline that had suddenly dropped several feet and been flooded by the ocean, burying ancient forests in saltwater mud. By dating these subsidence events, scientists discovered they occur, on average, every 300 to 500 years. The last one happened in January 1700. A fact confirmed by matching the geological record to a historical tsunami that struck Japan without any local earthquake to explain it. This research fundamentally rewrote the seismic hazard map for the entire region. It moved the Pacific Northwest from a low-risk zone to one capable of producing a magnitude 9.0 earthquake, forcing a complete overhaul of emergency preparedness plans, tsunami evacuation routes, and building codes for everything from skyscrapers to bridges. This is the profound power of paleoseismology. It gives communities a memory that stretches far beyond human history, providing the data needed to prepare for events so rare that no living person has ever experienced one. This historical detective work is now being supercharged by a suite of space-age technologies that allow us to watch the Earth strain and shift in real time. A vast network of continuous GPS stations anchored to bedrock across the globe measures movements as subtle as a few millimeters per year. These instruments can detect the slow, relentless buildup of strain along a locked fault, the silent loading of the spring before it eventually uncoils. Even more remarkable is a technology called InSAR, which uses radar satellites to scan the Earth's surface from space. By comparing radar images taken days or weeks apart, scientists can create incredibly detailed maps of ground deformation, revealing bulges, sinks, and creeping movements along faults that are completely invisible to the naked eye. This technology has unveiled a whole new class of seismic behavior, such as slow slip events or silent earthquakes, where a fault releases its built-up strain over weeks or months instead of seconds, without producing any shaking at all. While these events don't cause damage, they are critical clues in understanding the complex physics of fault friction and how stress is transferred through the crust, potentially bringing other, more dangerous fault segments closer to failure. The ultimate goal of all this monitoring is not to predict earthquakes with the precision of a weather forecast, a feat that remains beyond our current science, but to provide early warning. By detecting the first, fast-moving but less damaging seismic waves, P waves, the instant a quake begins, automated systems can now trigger alerts that travel faster than the slower, destructive waves, S waves. This can provide a precious few seconds to a minute of warning, enough time for surgeons to pause an operation, for trains to automatically slow down, for fire station doors to open, and for people to simply drop, cover, and hold on. This application of fault research, from the painstaking analysis of ancient trenches to the real-time data from satellites, has a single, profound purpose: to save lives and protect the infrastructure upon which modern society depends. It transforms our relationship with the ground beneath our feet from one of passive vulnerability to one of informed resilience, allowing us to build smarter and react faster in the face of the Earth's inevitable tremors. It's almost impossible to overstate just how revolutionary the theory of plate tectonics was for our understanding of the Earth. Before the 1960s, geology was a field filled with intriguing but disconnected observations, mysterious mountain ranges, puzzling fossil distributions, and strange magnetic patterns locked in seafloor rocks. Scientists had pieces of the puzzle, but they were missing the grand, unifying picture that could tie it all together. That picture finally emerged, and it was the humble, often overlooked fault that provided some of the most compelling and critical evidence to seal the deal. The patterns of movement recorded in these deep fractures didn't just hint at local geological stories. They screamed out the reality of massive, moving plates on a global scale, confirming a theory that had been ridiculed for decades. Think back to the early concept of continental drift, first proposed by Alfred Wegener in the early 20th century. He noticed the remarkable jigsaw puzzle fit of the Atlantic coastlines and pointed out that identical fossil plants and animals were found on continents now separated by vast oceans. His explanation was that the continents had once been joined in a supercontinent he called Pangaea and had since drifted apart, but without a mechanism to explain how these massive landmasses could plow through solid ocean crust. His idea was largely dismissed as geological fantasy. The missing proof wasn't in the continents themselves, but in the scars they left behind. Decades later, when geologists began meticulously mapping the fault systems of the Appalachian Mountains in North America and the Caledonian Mountains in Scotland and Norway, they found an incredible match. The types of faults, the direction of movement, the ages of the rocks, and the style of deformation were virtually identical. These two ranges, now separated by thousands of miles of ocean, were clearly once a single, continuous mountain belt, a colossal Himalayan scale range that had been formed by an ancient continental collision and then torn in two when the Atlantic Ocean began to open. The faults were the definitive forensic evidence, the smoking gun that proved Wegener was right all along. The continents had indeed moved, but the proof didn't stop there. As scientists began mapping the ocean floor in detail, they discovered a whole new class of faults that provided the final, irrefutable evidence for the mechanism of plate motion, transform faults. These are the spectacularly long, linear fractures that cut across the globe's mid-ocean ridges, the underwater mountain chains where new crust is constantly being created. At first glance, these faults seemed to simply offset the ridge, but a deeper look revealed something astonishing. The direction of motion along the fault was exactly opposite to what you would expect if it were just a simple crack sliding past itself. Seismic studies showed that the only place earthquakes were happening was in the segment between the two offset ridges. This precise pattern was predicted by the new plate tectonic theory. It was the result of two plates sliding past each other as they spread away from the ridge. It was a direct observation of the rigid plates in motion, a perfect confirmation of the model. These transform faults, like the famous ones intersecting the mid-Atlantic ridge, became the dashed lines we now see on every map of the Earth's tectonic plates, the boundaries where crust is neither created nor destroyed, but simply conserved as it grinds laterally. And then there are the faults that take us in the opposite direction, down into the Earth's depths. Subduction zones are perhaps the most dramatic expression of plate tectonics, and they are riddled with a complex network of faults that record the final descent of an oceanic plate. As a dense oceanic plate bends and dives beneath a continental plate, it doesn't just slide smoothly, it fractures, creating deep-seated faults that can generate the most powerful earthquakes on the planet. The study of these fault systems revealed the ultimate fate of the crust. It is recycled back into the mantle, completing the cycle that begins with the creation of new rock at the mid-ocean ridges. This discovery solved another great mystery: why the ocean floor was so relatively young, nowhere older than about 200 million years, while the continents contained rocks billions of years old. The faults in subduction zones were the answer. They are the planet's ultimate recycling centers, constantly consuming the old to make way for the new. This unifying theory, so powerfully supported by the evidence from faults, didn't just answer old questions, it completely transformed Earth science. It connected dots that had once seemed unrelated. It explained why the world's most violent volcanoes and earthquakes are not randomly scattered, but are neatly aligned along these plate boundaries, the Ring of Fire around the Pacific Ocean being the prime example. It showed that mountain building, volcanism, and seismicity are not isolated phenomena, but are all interconnected symptoms of a single planet-wide process, the slow, relentless motion of tectonic plates. This was the paradigm shift that turned geology from a science of cataloging local details into a predictive, global science. And even today, faults continue to be the primary tool for testing and refining these models. By studying ancient, inactive faults preserved in the interiors of continents, we can trace the history of plates that no longer exist and map the outlines of ancient oceans that have long since vanished. Every fault, whether a fresh scar on the landscape or an ancient stitch in the continental crust, adds another line to the story, showing us how movements from the deep past have irrevocably shaped the geology of our modern world. The story of our planet's continents doesn't begin with the famous Pangaea that every schoolchild learns about. It stretches back into a far more ancient and almost unimaginable past, to a time when the world was a truly alien place. Long before dinosaurs ever walked the Earth, even before complex life had fully emerged from the oceans, the continents were engaged in a slow, majestic dance of their own, periodically crashing together to form colossal supercontinents with names like Rodinia and Columbia, only to later tear themselves apart in spectacular fashion. And while these ancient landmasses have long since vanished, they left behind indelible fingerprints in the rock, the deep fault systems that act as our only reliable map to this lost world. These fractures are the archival records of collisions so ancient they make the formation of the Himalayas look like a recent event, and by learning to read them, geologists are essentially becoming cartographers of a planet that hasn't existed for over 1 billion years. To understand how this works, let's travel to a place like the Grenville province in eastern North America, a vast swath of rock that stretches from Labrador down to Texas. On the surface, it might just look like a rugged, heavily forested landscape, but to a geologist, it's an open book. The rocks here have been cooked and contorted by unimaginable heat and pressure, transformed into metamorphic gems like gneiss and marble. And running through them are ancient fault zones, the scars of a continental collision of epic proportions. This was the event that built the supercontinent Rodinia roughly 1,100,000,000 years ago. Imagine two proto-continents, ancient ancestors of what we now know as North America and Africa, slowly converging over tens of millions of years. The force of that collision would have been beyond comprehension, crumpling the crust for hundreds of miles, thrusting up a mountain range that might have rivaled the modern Himalayas, and driving faults deep into the planet's interior. The minerals within those faults, like stubborn zircons, locked in the timing of this event using their radioactive clocks, giving us a firm date for when this piece of the puzzle snapped into place. So when we study the Grenville faults, we're not just looking at a crack in some old rock. We are standing on the former suture zone, the very seam where two continents once welded themselves together to form a supercontinent. But one single seam isn't enough to map an entire vanished world. The real detective work begins when you pack your geological map and travel to another continent altogether. The incredibly precise matches are what make the theory so powerful. A geologist might be studying a fault system in eastern South America, in Brazil, and notice that the orientation of the fault, the type of movement it records, the age of the rocks involved, and the style of deformation are a perfect mirror image of a fault system she studied in Western Africa. It's like finding two pieces of the same ceramic plate that broke apart. The patterns on the edges match perfectly. This is the undeniable evidence that these two landmasses were once snugly joined together. By performing this painstaking correlation across the globe, matching fault patterns, mountain belt remnants, and ancient rock ages, researchers can slowly piece together the jigsaw puzzle of these supercontinents. They can start to draw tentative maps of what Rodinia or the even older Columbia might have looked like, showing how fragments of what are now India, Australia, and Antarctica were all nestled together in configurations that seem bizarre to our modern eyes. Understanding these cycles of assembly and breakup is about far more than just satisfying our curiosity about ancient geography. It's fundamental to understanding the entire history of our planet's environment. The arrangement of continents on the globe is the primary control knob for climate over geological time. A single, large supercontinent like Rodinia would have had a vastly different climate than our modern world of scattered continents. Its immense size would have created sprawling, searing hot deserts in its vast interior, far from the moderating influence of the ocean. Coastlines would have been limited, affecting the patterns of rainfall and the productivity of marine life. When such a supercontinent eventually ruptured, it would have been a world-changing event. New ocean basins would form as the fragments drifted apart, completely altering ocean currents. These currents are the planet's circulatory system, distributing heat from the equator to the poles. A new current could turn a frozen wasteland into a temperate forest or vice versa. Furthermore, the process of rifting itself involves massive volcanic activity, pumping enormous quantities of carbon dioxide and other gases into the atmosphere, potentially triggering intense greenhouse warming periods. Conversely, the uplift of new mountain ranges during continental collisions accelerates the weathering of rock. a process that pulls carbon dioxide out of the atmosphere and can lead to global cooling and even ice ages. The very evolution of life was likely influenced by these cycles. The breakup of a supercontinent creates new coastlines, new shallow seas, and new isolated environments, all of them potential catalysts for the evolution of new species. The rise of complex animal life during the Cambrian explosion is thought by many to be linked to the fragmentation of the supercontinent Pannotia, which preceded Pangaea. The faults that record these titanic events are therefore not just geological features. They are the key to understanding why our planet's climate has veered between tropical hothouse and frozen snowball, and how the stage was set for the explosion of life that led, eventually, to us. Of course, reading this billion-year-old story is incredibly difficult. These ancient fault systems are rarely pristine. They are more like a palimpsest, an ancient parchment that has been scraped clean and written over multiple times. A single fault zone in the heart of a continent might have first formed during the assembly of Rodinia, only to be reactivated hundreds of millions of years later during the formation of Pangaea, and then yet again during a much later tectonic event. Each episode of movement can overprint and obscure the evidence of the previous one. Unraveling this history requires the most sophisticated tools of geochemistry, geochronology, and structural geology to tease apart the different events, to figure out which mineral grew when, and which direction the rock moved during each separate chapter of its long and violent history. It is the ultimate geological cold case, but the payoff is a revelation of the deepest rhythms of our planet, the slow, grand cycles that dictate the long-term fate of the climate and the biosphere. How do you test a theory about forces so immense they can move continents and processes so slow they take millions of years to unfold? You can't just wait around to watch a mountain range form. This is where the science of geology gets incredibly creative, moving from the field to the laboratory. To truly understand the hidden mechanics of deep faults, researchers have developed brilliant ways to literally play in the sandbox. Using scaled-down analog experiments and sophisticated computer simulations, they can compress millions of years into minutes, allowing them to observe the birth and evolution of faults right before their eyes. These models are far more than simple demonstrations. They are critical tools for testing hypotheses about how rock behaves under the incredible stresses found deep within the Earth's crust. One of the most visually compelling methods is the analog sandbox experiment. Picture a large, transparent box filled with alternating layers of colored sand and clay, each layer representing different types of sedimentary rock with varying strengths. Then imagine a movable wall at one end of the box that slowly, incrementally pushes inward, simulating the tectonic forces of continental collision. As the compression builds, the once flat layers begin to deform. You can actually watch it happen. First, a gentle fold appears in the sediment. Then, as the pressure becomes too great, a tiny crack forms. This crack doesn't just sit there. It grows, angling backward and eventually thrusting one section of the layered material up and over another. In a matter of minutes, the experiment replicates the entire life cycle of a thrust fault system, creating a perfect miniature version of a fold and thrust belt just like those seen in the Canadian Rockies or the Italian Apennines. By changing the variables using finer or coarser sand to represent stronger or weaker rock, or introducing a thin layer of silicone to simulate high-pressure fluids that lubricate the fault, scientists can see how these factors control the final shape of the mountain belt, the spacing between faults, and the angle at which they dive into the subsurface. While sandboxes are fantastic for visualizing the big-picture structural patterns, they can't easily capture the complex physics of individual earthquakes or the precise role of temperature and pressure at great depths. This is where the power of computational modeling takes over. Geologists and geophysicists write complex algorithms that describe the laws of physics, the mechanics of rock deformation, the flow of fluids, and the transfer of heat, and then set these equations loose inside a supercomputer. They can create a virtual fault zone and apply digital stress to it, watching as it predicts exactly how and where the rock will likely break. These numerical simulations allow for a level of precision that physical models can't match. A researcher can ask the computer, what happens if the strain rate is twice as fast? Or, how does a high fluid pressure change the angle of the fault? And get an immediate, detailed answer. This is incredibly valuable for understanding the triggers of earthquakes. By simulating the buildup of stress along a locked fault and the sudden release of that stress in a slip event, these models help identify the conditions that might push a stable, creeping fault into a violent, catastrophic rupture. The ultimate goal of all this modeling, both physical and digital, is prediction. By understanding the fundamental rules that govern fault behavior, scientists can move beyond simply describing what has already happened to forecasting what might occur in the future. For a geologist assessing seismic hazard, these models can help predict how a fault network might reactivate. An ancient, seemingly dormant fault might be dangerously vulnerable if new tectonic stresses are applied to it in just the right way. Models can show how the rupture from one earthquake might transfer stress to a neighboring fault, bringing it closer to its own breaking point, a crucial insight for assessing risk in a complex system like California. For those in resource exploration, the applications are equally profound. The models can predict how a fault might act as a seal, trapping a reservoir of oil or gas on one side, or conversely, how it might serve as a conduit, channeling mineral-rich fluids to form an ore deposit. This knowledge helps guide the extremely expensive decision of where to drill, turning geological theory into economic reality. By bridging the vast gap between direct observation and theoretical understanding, these experimental models provide a powerful window into processes that are otherwise utterly inaccessible, allowing us to test the very forces that shape our world. This deep understanding of fault mechanics moves from the theoretical to the intensely practical the moment we decide to build anything of significance. The ground we construct upon is not a passive, stable canvas. It is a dynamic system, and when that system includes an active fault, the risks to human infrastructure are profound. A dam sitting astride a fracture line isn't just a structure. It's a potential catastrophe waiting for the next seismic event, threatening downstream communities with a devastating wall of water. A tunnel bored through an active fault zone could be sheared in two, severing a critical transportation or utility link. A pipeline carrying oil or gas could rupture, leading to environmental disaster and economic disruption. This isn't a hypothetical fear, it's a reality that geotechnical engineers and urban planners confront every single day. Their work is a powerful fusion of deep-time geological insight and cutting-edge human ingenuity, all aimed at one goal: making our modern world resilient to the ancient, powerful forces that shape it. The first and most crucial line of defense is simply avoidance. Before a single foundation is poured, teams of geologists and engineers meticulously scour detailed fault maps, combining satellite imagery, aerial photography, and good old-fashioned fieldwork to identify the precise location of active faults. They're not just looking for the obvious scarps, they're searching for subtle signs, offset stream channels, linear valleys, and tiny, slow-moving cracks in the ground that betray a fault's presence. This is where paleoseismology, the science of reading past earthquakes from trench exposures, becomes a vital planning tool. By understanding a fault's recurrence interval, the average time between major quakes, and its potential maximum magnitude, planners can establish setback zones. These are legally mandated buffers around a known fault where certain types of construction, especially for critical facilities like hospitals, schools, or nuclear power plants, are either heavily restricted or completely prohibited. This proactive approach, born directly from our ability to read Earth's seismic history, is the simplest and most effective way to prevent a tragedy before it can ever begin. But we can't simply abandon entire cities or avoid routing essential infrastructure across vast regions of the planet that are seismically active. This is where engineering brilliance takes over, designing structures that can dance with the earthquake rather than try to rigidly resist it. One of the most revolutionary innovations in this field is base isolation. Imagine placing an entire building on a set of massive, flexible bearings, often made from alternating layers of steel and rubber, that are installed between the foundation and the superstructure. When the ground suddenly lurches during an earthquake, these isolators absorb and deflect the energy, allowing the building to slide back and forth gently atop them while the ground beneath moves violently. The building essentially floats on its seismic shock absorbers, dramatically reducing the shaking experienced by the structure and everything inside it. This technology has been used to protect everything from city halls and hospitals to museums housing priceless artifacts, and it represents a fundamental shift in design philosophy. Instead of fighting the force, you yield to it gracefully. Perhaps one of the most elegant and visible examples of this design for movement principle is the Trans-Alaska Pipeline. This 800-mile-long artery for crude oil crosses 3 major mountain ranges and no fewer than 3 active fault lines. The engineers faced an impossible dilemma. How do you design a rigid steel pipeline to survive a fault rupture that could suddenly offset the ground by 15 or 20 feet beneath it? Their solution was as simple as it was ingenious. Where the pipeline crosses the notorious Denali Fault, it wasn't buried or anchored firmly in place. Instead, it rests on specially designed slidable support beams. These beams are topped with Teflon-coated shoes that allow the pipe to slide freely sideways. In the event of a major earthquake, the ground on one side of the fault can lurch horizontally, but the pipeline simply slides along these rails, bending into a wide, gentle curve that prevents it from kinking, breaking, and spilling millions of gallons of oil into a pristine wilderness. This system was put to the ultimate test in 2002 when a magnitude 7.9 earthquake tore right across the Denali Fault. The ground shifted nearly 15 feet, but the pipeline slid as designed, bending and flexing without rupturing. It was a stunning victory for applied geology and engineering, a direct and successful application of understanding fault mechanics to protect both the environment and a vital economic resource. This is the ultimate payoff for deciphering Earth's secret past. It gives us the knowledge to build a safer, more resilient future, living in harmony with the dynamic planet we call home. While the painstaking work of trenching and mapping gives us a deep historical record, the real revolution in understanding fault behavior is happening right now in real time from the vantage point of space. We've moved beyond simply reading the past. We are now learning to sense the present and anticipate the future with a suite of technologies so precise they can measure the Earth straining and sighing by mere millimeters. This isn't science fiction. It's the new reality of fault monitoring, a field transformed by satellites, supercomputers, and sophisticated sensors that are turning geology into a predictive science. At the forefront of this revolution is a remarkable technology called interferometric synthetic aperture radar, or in SAR for short. Imagine a satellite orbiting high above the Earth, constantly sending down pulses of radar energy and meticulously recording the signals that bounce back from the surface. It does this over and over, month after month, building a repetitive, incredibly detailed map of the ground's exact position. By comparing these radar maps over time, scientists can detect changes in the distance between the satellite and the ground with an accuracy that is almost unbelievable. They can see the land rising, falling, or shifting sideways by less than the width of a pea. This allows them to watch the crust deform in the years, months, and even days leading up to a seismic event, mapping the silent buildup of strain along a locked fault with a clarity that was once impossible. But in SAR's most startling discovery has been the phenomenon of slow slip events, or silent earthquakes. Along subduction zones like those in the Pacific Northwest or Japan, this technology has revealed that faults don't always release their pent-up energy in a violent, minutes-long rupture. Sometimes they let it go in a slow, silent creep that can last for weeks or even months, moving the equivalent of a magnitude 7 earthquake's worth of energy without producing a single perceptible tremor. This hidden world of tectonic motion completely upends our traditional models of how faults behave and is critical for understanding how stress is transferred to adjacent, potentially more dangerous segments of a fault system. This space-based eye in the sky is powerfully complemented by a vast, ground-truthing network of permanent GPS stations anchored firmly to bedrock across the world's fault zones. These aren't the GPS units in your car or phone. They are ultra-precise scientific instruments that measure their own position 24 hours a day, 7 days a week, with millimeter-level accuracy. This dense network acts like a giant strain meter for the planet's crust. By tracking the subtle, relentless movement of these stations, the slow northwest drift of Oregon, the gradual compression of the Los Angeles Basin, scientists can map the elastic strain accumulating as tectonic plates grind against each other. They can see a region slowly bulging upward by a few millimeters each year, a clear sign that strain is building and the fault is locked, storing energy that will eventually have to be released. This continuous, real-time data is the numbers behind the intuition, providing the hard metrics that feed into our hazard models and helping to pinpoint which sections of a fault are under the greatest stress and may be nearing their breaking point. And the data from these tools is so immense and complex that the human brain alone can't hope to spot all the subtle patterns hidden within it. This is where the power of artificial intelligence and machine learning enters the picture. Researchers are now training sophisticated algorithms to sift through mountains of data, decades of seismic readings, decades of GPS time series, terabytes of SAR imagery to find the faint signals that might precede a major earthquake. These algorithms can detect correlations that would be invisible to us, perhaps identifying a specific pattern of tiny, precursor tremors or a particular rate of crustal deformation that has, in the past, reliably preceded a larger event. While we are still far from reliable short-term earthquake prediction, these machine learning models are getting progressively better at medium-term forecasting, helping to refine probabilistic models that tell us not when an earthquake will happen, but how the odds of one occurring are changing over time. For the final, fine-scale mapping of the fault lines themselves, technology has taken to the skies with drones equipped with LiDAR scanners. LiDAR works by firing millions of laser pulses at the ground and measuring the time it takes for each one to return, building a fantastically detailed, three-dimensional map of the Earth's surface. When flown over a forested fault zone, the LiDAR can digitally strip away the vegetation, revealing the bare earth beneath and exposing the subtle topography of the fault, the scarps, lineations, and offset streams that are hidden from the naked eye. This allows geologists to map the precise location and recent history of faults in remote, rugged, or densely vegetated terrain with a speed and accuracy that would have taken years of difficult fieldwork just a generation ago. The ultimate goal of all this technological integration is to save lives through earlier warning. Systems like Shake Alert on the U.S. West Coast leverage the instant data from seismometer arrays. When a quake begins, the system detects the fast-moving but less damaging P waves and calculates the location and magnitude within seconds, sending an alert that can travel faster than the slower, destructive S waves. This might only provide a few seconds to a minute of warning, but that is enough time for life-saving actions, for trains to automatically brake, for surgeons to pause delicate operations, for people to drop, cover, and hold on. This shift from historical analysis to near real-time monitoring and proactive warning represents a quantum leap in our relationship with the planet's dynamics, transforming us from passive victims of natural forces into informed and resilient communities. We often think of the Earth's major systems as operating independently, the solid ground shifting through tectonics, the atmosphere changing through climate cycles. But one of the most fascinating revelations in modern geoscience is just how deeply interconnected these processes truly are. It turns out that the air and the rock are in a constant, slow-motion conversation, each capable of influencing the other over both short and astonishingly long timescales. While we've long understood that tectonic forces can dramatically reshape climate by building mountains that alter wind and rain patterns, a new and more surprising question is now being asked. Could the rapid climate changes we're driving today actually influence the very behavior of the faults and plates beneath our feet? Emerging research suggests the answer is a tentative yes, revealing a delicate and complex feedback loop between the sky above and the rock below. Consider the profound weight of a continental ice sheet. Imagine a layer of ice 2 miles thick, like the one that once smothered much of North America and Northern Europe during the last ice age. That ice represented an enormous load, literally pressing down on the continental crust and causing it to sag, much like a person sitting on a firm mattress. But when the climate warmed and those massive glaciers began to melt away, that immense weight was lifted. The crust, no longer suppressed, began to slowly spring back upward in a process known as glacial isostatic adjustment or post-glacial rebound. This isn't just a theoretical uplift, it's something we can measure with incredible precision using GPS. In places like Scandinavia and Canada, the land is still rising today, over 10,000 years after the ice retreated, at a rate of about a centimeter per year. But this rebound is more than just a gradual, peaceful rise. As the crust adjusts, it flexes and bends, subtly altering the stress fields acting on ancient faults buried deep within. This can be enough to reactivate faults that have been dormant for millennia, producing small but measurable earthquakes. In otherwise stable regions like eastern Canada and northern Europe, this climatically triggered seismicity is a direct link, a change in the atmosphere and cryosphere reaching down and nudging the solid Earth into motion. The influence doesn't stop with melting ice. A warmer atmosphere holds more moisture, leading to increased rainfall and more intense storms in many parts of the world. This heightened precipitation supercharges the forces of erosion. Rivers carry more sediment away from mountain ranges, and landslides become more frequent, effectively stripping mass from the tops of mountains and redistributing it to valleys and ocean basins. This large-scale shifting of weight from one place to another can also change the stress on faults. By lightening the load on a mountain range, erosion can reduce the downward force that helps clamp a fault shut, potentially making it easier for the fault to slip. Conversely, the deposition of vast amounts of sediment in a delta or basin can increase the load there, potentially putting pressure on faults in that area. It's a planetary scale balancing act, where the washing away of dirt and rock by rain and rivers can, over time, have a tangible impact on the likelihood of an earthquake. While the effect is subtle and operates over long timescales, it underscores that human-caused climate change isn't just a surface issue. Its consequences may resonate deep into the crust. But this conversation between rock and sky is a two-way street, and the tectonic side of the equation has been shaping the climate for eons. This brings us to one of the most important long-term climate stabilizers on Earth, the weathering thermostat. It works like this: when tectonic forces thrust up a major mountain range like the Himalayas, they expose vast amounts of fresh, unweathered rock to the atmosphere. Rainwater, which is naturally slightly acidic because of dissolved carbon dioxide, falls on these rocks and triggers a chemical reaction called silicate weathering. Essentially, the rain slowly eats away at the rock, and in the process, it pulls carbon dioxide out of the atmosphere. The products of this reaction are eventually washed into the oceans, where the carbon is locked away in carbonate rocks on the seafloor for millions of years. The incredible result of this process is that mountain building actually cools the planet down by drawing down greenhouse gases. It's a negative feedback loop. If the Earth gets too warm, weathering rates tend to increase, pulling more CO2 out of the atmosphere and moderating the temperature. This process is a leading theory for why Earth's climate has remained relatively stable and habitable for billions of years, allowing life to persist. Understanding these deep interconnections is no longer just an academic exercise. It's becoming a critical component of hazard assessment. As we continue to warm the planet at an unprecedented rate, we are conducting a massive, unplanned experiment on the Earth system. The accelerated melting of the Greenland and Antarctic ice sheets is causing rapid crustal uplift not just in polar regions, but also a complex seesaw effect globally, as the redistributed water alters the planet's gravitational field and rotation. Could this potentially influence fault systems far from the ice? The increased frequency of extreme rainfall events is accelerating erosion in mountain ranges worldwide. Might this subtly alter the stress on major fault zones like the San Andreas over centuries? We don't have definitive answers yet, but the research is pointing toward a future where climate change could have indirect and profoundly important geological consequences. This holistic view forces us to see our planet not as a collection of separate parts, but as a single, deeply integrated system where a change in one realm can ripple through all the others in surprising ways. While the slow grind of tectonic plates and the gradual forces of erosion shape our world over eons, the Earth's history is also punctuated by moments of unimaginable, instantaneous violence cataclysms that reshape the planet in a matter of minutes or even seconds. And remarkably, the silent, stony archives of deep fault zones have preserved vivid forensic evidence of these ancient catastrophes. These aren't just the scars of routine earthquakes. These are the indelible marks left by events of truly biblical proportions, from asteroid impacts that wiped out entire dynasties of life to mega-quakes that sent ocean-spanning tsunamis crashing onto shores. By learning to read this specific language of destruction, geologists can essentially bear witness to the worst days in our planet's history. One of the most dramatic pieces of evidence for a high-energy impact is something called a shatter cone. These are not mere broken rocks. They are exquisite, conical fracturing patterns that fan out through bedrock like the shockwaves they represent. Picture the precise, swirling fracture you might see in a shattered car windshield, but scaled up and etched into solid granite. These distinctive patterns only form under the immense, instantaneous pressure of a hypervelocity impact, the kind generated when a miles-wide asteroid slams into the Earth at tens of thousands of miles per hour. The force is so beyond anything produced by tectonic processes that it leaves this unique calling card. Finding a shatter cone in an ancient rock layer is like finding the bullet hole at a crime scene. It's definitive proof that an impact occurred, allowing scientists to locate and confirm even heavily eroded craters that have been hidden by millions of years of subsequent geology. Inside the fault zones themselves, another astonishing signature can be found, a rock called pseudo-tachylite. The name itself is a clue. Tachylite is a volcanic rock, and pseudo means false. So, false volcanic rock, that's exactly what it is. During an incredibly powerful earthquake, the friction generated along a fault can be so intense that the rock on either side doesn't just grind, it instantaneously melts. This friction melt, which can reach temperatures of over 2,000 degrees Fahrenheit, is then squirted and injected into the surrounding fractures, where it rapidly cools and solidifies into a dark, glassy vein. Pseudo-tachylite is the frozen remnant of a frictional meltdown, a literal flash in the pan on a geological scale. Finding it tells a geologist that they are looking at the epicenter of a truly enormous ancient seismic event, one so powerful it turned solid stone into liquid fire for a fleeting moment. The most profound example of a global catastrophe etched into faults is undoubtedly the Chicxulub impact, the city-sized asteroid that struck off the coast of Mexico 66 million years ago, ending the age of the dinosaurs. The immediate effects were apocalyptic firestorms, global darkness, and a devastating impact winter. But the energy released was so colossal that it didn't just create a crater. It sent seismic shockwaves rippling across the entire planet, equivalent to an earthquake thousands of times more powerful than any ever recorded by humans. This global shaking would have violently reactivated faults everywhere, from the mid-ocean ridges to continental rift valleys. Evidence for this simultaneous, worldwide seismic paroxysm is now being found in deep-sea marine cores. Sediment layers that were being deposited quietly on the ocean floor that very day show sudden, dramatic disturbances, slumps, and slides triggered by the intense shaking, all occurring at the exact same geological instant, the boundary between the Cretaceous and Paleogene periods. The faults themselves, in areas far from the impact site, show signs of movement and injection of fluids that are dated to this time, recording the planet's crust shuddering in response to a blow from outer space. Faults also hold the key to understanding the recurring threat of another type of catastrophe, the mega-tsunami. In subduction zones where one tectonic plate dives beneath another, the most powerful earthquakes on Earth can occur. These megathrust quakes don't just shake the ground, they suddenly lift up a massive section of the seafloor by several meters, displacing an enormous volume of water and sending a series of devastating waves racing across the ocean. While the earthquake's energy dissipates quickly, the evidence of the tsunami it generates can be preserved for millennia. Geologists hunt for this evidence in coastal areas near these faults, digging trenches into low-lying coastal plains and marshes. What they look for are telltale sheets of sand, often filled with shells and ocean debris, sandwiched between layers of peat and soil. Each of these sand layers represents a moment when the ocean violently inundated the land, a tsunami deposit. By carbon dating the organic material just below and above these sand layers, researchers can determine exactly when these past tsunamis occurred, and by correlating these sand sheets across different sites, they can even begin to estimate the wave's height and run-up distance. This work has been crucial in places like the Pacific Northwest, where it revealed the ancient history of the Cascadia subduction zone, and in Japan, where it helped confirm the historical frequency of devastating waves, leading to significantly improved coastal defense and evacuation plans. This paleoseismology doesn't just tell stories about the past, it provides the data we need to save lives in the future, turning ancient faults into early warning systems written in stone and sand. But our planet's story of faults and fractures is just one chapter in a much larger cosmic saga. To truly appreciate the unique geological personality of Earth, we need to leave its surface behind and journey to other worlds, where we find familiar features shaped by entirely alien processes. The study of faults isn't confined to our home planet. It's a universal tool for deciphering the history of any rocky body in our solar system and beyond. By comparing the cracks and scars on other planets to those we know so well on Earth, we gain a powerful new perspective, revealing not just how other worlds work, but what makes our own so special. This field, known as comparative planetology, turns our solar system into a grand natural laboratory, with each planet and moon offering a different experiment in planetary evolution. Take Mars, our rust-colored neighbor. From orbit, one feature dominates the landscape near its equator, Valles Marineris. This isn't just a canyon, it's a canyon system on a monstrous scale, so vast it could stretch across the entire continental United States, with depths that make the Grand Canyon look like a mere scratch on the surface. For a long time, scientists debated its origins. Was it carved by water? While water may have later modified it, the primary cause is now believed to be tectonic stretching. Valles Marineris is essentially a gigantic rift valley, a place where the crust of Mars was pulled apart billions of years ago, creating a series of colossal normal faults that dropped massive blocks of terrain down between them. This suggests that early Mars was a much more geologically active world, possibly with a hotter interior that allowed for some form of large-scale crustal movement. However, the absence of a long, continuous plate boundary system like Earth's mid-ocean ridges indicates that Mars never developed the full, recycling engine of plate tectonics that drives so much of our planet's geology. Its faults are the frozen remnants of a past era of activity, a world that has since cooled and geologically quieted down, its internal engine seizing up. Then there's Mercury, the solar system's smallest and innermost planet. Despite its diminutive size, it holds a massive surprise. Writhing across its crater-battered surface are long, sinuous cliffs called lobate scarps. These aren't the result of the crust being pulled apart, they are the opposite. They are thrust faults formed by compression, where one section of the planet's crust has been pushed up and over another. The incredible implication here is that the entire planet is shrinking. As Mercury's massive iron core cooled over billions of years, it contracted, causing the outer rocky shell to crumple and crack like the skin of a drying apple. These globally distributed scarps tell a story of a one-plate planet whose entire geological history has been dominated by this global contraction, a process that still might be causing tiny Mercuryquakes today. It's a stark contrast to the diverse and dynamic faulting we see on Earth. This comparative work is far more than just remote observation from orbit. We are now placing ears on the ground to listen to the faint tremors of other worlds. NASA's InSight lander mission to Mars was a revolutionary step in this direction. Its primary instrument was a highly sensitive seismometer designed to detect Mars quakes. By analyzing the seismic waves from these quakes as they traveled through the Martian interior, scientists could pinpoint their source and determine if they were caused by movement along faults or by other processes, like magma moving deep underground or even meteorite impact. The data from InSight confirmed that Mars is indeed seismically active, though far quieter than Earth. These gentle rumblings are like a sonogram of the planet's interior, helping us map its internal structure and understand the forces still at work within it. Each detected Mars quake adds another piece to the puzzle, helping explain why a planet so similar in structure to Earth ended up on such a different geological path. The ultimate lesson from this cosmic comparison is the critical role of water and size. Earth's active plate tectonics, its abundant and diverse fault systems, and its continuous geological renewal seem to be fueled by two key ingredients. It is large enough to retain a hot, energetic interior, and it is wet. Water trapped within Earth's minerals acts as a lubricant, lowering the melting point of rock and facilitating the ductile flow that allows plates to slide and subduct. Mars, being smaller and colder, lost its internal heat too quickly and likely never had enough water in its crust to lubricate a full tectonic cycle. Mercury, though possessing a large core, is simply too small and dry. This cosmic perspective is profoundly humbling. It shows us that Earth's dynamic nature, with its quakes and eruptions that both threaten and renew, is not the standard model for a rocky planet. It may, in fact, be a rare and special condition, a delicate balance of size, composition, and perhaps even the presence of water that creates a world capable of supporting a rich and enduring biosphere. By studying the silent, frozen faults on our planetary cousins, we don't just learn about them, we gain a deeper, more precious understanding of the unique and vibrant world we call home. But the story of what happens deep within a fault zone isn't just about solid rock grinding against itself. There's a silent, powerful third character in this geological drama: fluids. Imagine the intense pressure and heat miles below your feet. Under these extreme conditions, water, superheated steam, magma, and mineral-rich hydrothermal solutions are not passive bystanders. They are active, dynamic agents that fundamentally control how faults behave. Their presence can be the difference between a fault that creeps along silently for centuries and one that locks up for millennia before unleashing a catastrophic earthquake. This hidden world of fluid-rock interaction adds a breathtaking layer of complexity to our understanding of the planet's mechanics, revealing that the most powerful forces shaping our world are often mediated by the most common substance of all: water. One of the most direct ways fluids influence faults is by dramatically reducing friction. Picture the immense weight of rock pressing down on both sides of a fault. For it to slip, enough stress must build up to overcome the sheer friction of granite grinding on granite. Now, introduce high-pressure fluids into that equation. These fluids, trapped within the pore spaces of the rock, can push back against the immense overburden pressure. This effectively lifts the two blocks of rock ever so slightly, reducing the normal force clamping them together, a process geologists call pore fluid pressure. It's akin to hydroplaning. A thin layer of water between a car's tire and the road eliminates traction, allowing the tire to slide effortlessly. In the same way, a fault saturated with high-pressure fluid can slip with far less tectonic stress. This isn't just a theoretical concept, it's a phenomenon we've unintentionally proven through human activity. The dramatic rise in induced seismicity, earthquakes caused by industrial processes in places like Oklahoma, is a direct result of this. Wastewater from oil and gas operations is injected deep underground under high pressure, where it migrates into ancient fault zones. This injected fluid increases the pore pressure, effectively lubricating faults that were previously stable and triggering earthquakes that otherwise might not have occurred for thousands of years. It's a sobering demonstration of how sensitively the Earth's crust can respond to changes in its fluid pressure. Yet, these same fluids are also master architects of immense beauty and economic value. In the slower, more peaceful periods between earthquakes, those same hydrothermal solutions are constantly circulating through the fracture networks. Heated by the Earth's internal warmth, these fluids act as universal solvents, leaching out valuable metals like gold, silver, copper, and zinc from the surrounding rock. As they travel upward along the fault zone, they encounter changes in temperature, pressure, or chemistry that force them to drop their dissolved mineral cargo. Over millions of years, this slow, persistent process can transform a simple fracture into a rich vein of ore, a glittering metallic deposit that has fueled human ambition and built economies. The legendary Comstock lode in Nevada or the vast copper porphyry deposits of Chile are all testament to this mineral precipitating power of fault-controlled fluid flow. The very same geological plumbing system that can unleash destruction is also responsible for concentrating the resources that power our modern world. Perhaps the most profound role of fluids is seen in the planet's most powerful earthquake factories, subduction zones. Here, as an oceanic plate bends and dives beneath a continental plate, it doesn't go down alone. The descending slab is covered in a layer of water-rich sediments and hydrated minerals clays that have formed on the seafloor over millions of years. As the plate is driven deeper into the Earth's mantle, it is subjected to ever-increasing heat and pressure. This forces the water out of the minerals in a process called dehydration. This released water doesn't just disappear, it rises upward into the hot mantle rock of the overlying plate. The effect is transformative. Water drastically lowers the melting point of mantle rock, causing it to partially melt and generate the magma that feeds the iconic volcanoes of the Pacific Ring of Fire from Mount St. Helens to Fuji, but the influence goes even deeper. The fluids also percolate into the interface between the two plates, the mega fault itself. Here, they can create conditions of extremely high pore pressure, lubricating the fault and facilitating the slow, silent creep that characterizes some parts of a subduction zone. However, they can also contribute to building the terrifying strain that leads to a megathrust earthquake. The complex interplay between the release of fluids, the creation of melt, and the mechanics of the fault is one of the most active and critical areas of geological research today, as it holds the key to understanding where and when the planet's most powerful quakes might strike. Ultimately, understanding this intricate dance between rock and fluid is what allows scientists to move from simply observing faults to truly predicting their behavior. It helps explain the puzzling patchwork of seismic activity we see, why one segment of a fault might be constantly slipping and harmless, while an adjacent segment, perhaps starved of these lubricating fluids, remains locked and dangerous, building up strain for a future large earthquake. For resource exploration, this knowledge is equally vital. It allows geologists to model where those metal-rich fluids were most likely to have deposited their treasure, guiding the search for the next generation of mineral deposits. The presence, pressure, and composition of fluids add a dynamic and crucial variable to the equation of our planet's behavior, showing us that the solid Earth is, in many ways, profoundly wet. Unlocking the full story hidden within a deep fault is like trying to solve the world's most complex puzzle, and no single scientist holds all the pieces. The most profound revelations come when experts from wildly different fields bring their unique tools to the same rocky outcrop, each interpreting a different part of the language written in the stone. A geologist might see the broad brushstrokes of the fault's history in the folded and fractured rock layers, but it takes a geochemist with a mass spectrometer to read the fine print. By analyzing the isotopes' slightly different atomic versions of elements like oxygen or carbon, trapped within minerals that grew during the faulting event, these scientists can act as forensic detectives. They can determine the precise temperature and pressure conditions at the moment the rock broke, or trace the origin of ancient fluids that once coursed through the fracture, revealing whether they were born from meteoritic rainwater, magma, or even the deep mantle. This chemical evidence transforms a qualitative story into a quantitative one, providing hard numbers on the immense forces at play millions of years ago. Meanwhile, in the deepest, darkest fractures where water and nutrients are scarce, biologists are making discoveries that push the boundaries of what we consider possible for life. They've found entire ecosystems of microbes known as extremophiles thriving in these intense environments. These hardy organisms, living off chemical energy from rocks like pyrite or methane rather than sunlight, are more than just a curiosity. They represent a potential analog for the earliest life on Earth, which may have originated in similar protected, chemosynthetic environments deep in the crust. But the implications stretch even farther into the cosmos. If life can persist in the crushing pressure and searing heat of a fault zone miles below our feet, it could very well exist in the subsurface fractures of Mars or in the global ocean hidden beneath the icy shell of Jupiter's moon Europa. The study of these deep biospheres, therefore, isn't just about biology. It's a crucial piece of astrobiology, helping us define the habitable zone for life not just on planets but within them. To understand the immense structures that house these microbes and guide these fluids, we need to see inside the Earth, and that's the domain of the geophysicist. Using a technique called seismic tomography, they essentially create a CT scan of the planet's interior. This process relies on the energy waves released by earthquakes, which travel through the Earth at different speeds depending on the temperature, density, and physical state of the rock they move through. By deploying vast arrays of sensitive seismometers and recording how these waves are bent, slowed, or accelerated, geophysicists can reconstruct a three-dimensional image of a fault zone at depths we could never hope to drill. This allows them to map the dipping angle of a subducting plate, identify vast reservoirs of magma, or locate areas of serpentinized rock, a water-rich mineral that lubricates faults, all from the surface. This imaging is the foundational map upon which all other disciplines overlay their data. Finally, bringing all this field observation, chemical analysis, and geophysical imaging together falls to the computational modelers and engineers. They take this mountain of multidisciplinary data and use it to build sophisticated digital simulations of fault behavior. These aren't simple animations, they are complex mathematical models that incorporate the laws of physics, rock mechanics, and fluid dynamics. An engineer can input data about rock strength from a geologist, fluid pressure from a geochemist, and a fault geometry from a geophysicist, and then run simulations to see how the entire system responds to increasing tectonic stress. Will the fault creep harmlessly? Will it lock up and store dangerous energy? How will fluids migrate and potentially trigger a rupture? These models allow scientists to perform virtual experiments that would be impossible in the real world, testing hypotheses and predicting behavior in a way that continuously refines our understanding. This powerful synergy, where a biologist's discovery in a deep fracture can influence an engineer's model of fault lubrication, is what truly accelerates our discoveries, proving that the deepest secrets of our planet are only revealed when we work together. For centuries, geology was a science practiced by experts in remote field locations, their findings published in academic journals read by a select few. But a powerful shift is underway, one that recognizes that the ground beneath our feet is a shared inheritance and that understanding its secrets shouldn't be locked away in university libraries. Today, the world of fault research and earthquake science is being thrown wide open, inviting everyone to become a participant in discovery. This movement towards public engagement and citizen science transforms abstract geological concepts into tangible, hands-on experiences that build a more informed and resilient society. Documentaries and museum exhibits serve as the grand gateways to this world. A breathtaking IMAX film that takes viewers on a virtual journey deep into the San Andreas Fault, or a museum diorama that lets you stand on a shaking platform to simulate the 1906 San Francisco earthquake, does more than just entertain. They translate millions of years of complex tectonic history into a visceral, emotional experience. When you feel the virtual ground rumble and see computer-generated visuals of seismic waves pulsing through the Earth, you're not just learning about plate tectonics, you're feeling it. This emotional connection is the first and most crucial step in transforming public perception from one of passive fear to one of active understanding. It demystifies the science, replacing the terrifying unknown with a framework of knowledge. Suddenly, an earthquake isn't just a random act of God. It's a predictable, understandable consequence of our planet's dynamic nature. This foundational awareness is what motivates a person to then download an app, attend a community preparedness meeting, or even contribute their own observations. And that's where the real revolution is happening, in the palm of your hand. Smartphone apps like the US Geological surveys, did you feel it? Program have turned millions of people into a distributed, real-time seismic sensor network. When the ground shakes, instead of just posting about it on social media, people can immediately report their location, the intensity of the shaking, and even the effects they observed. This crowdsourced data is invaluable. While sensitive scientific instruments measure the earthquake's magnitude at its source, these thousands of individual reports create a detailed map of the shaking intensity, called a shake map. This map shows scientists and emergency managers exactly where the strongest damage likely occurred, which bridges might be compromised, and which hospitals experienced the most severe shaking, allowing for a far more efficient and targeted emergency response. It turns every citizen into a crucial node in the network of community safety. The engagement goes even deeper for those who want to don the virtual hard hat of a geologist. Online citizen science platforms, such as those hosted by Zooniverse, present volunteers with high-resolution satellite imagery of landscapes known to be cut by faults. The task might be as simple as tracing a linear feature across a hillside or identifying signs of recent ground movement. The human brain is exceptionally good at pattern recognition, often outperforming algorithms at spotting these subtle clues. By enlisting an army of dedicated volunteers to scan thousands of square miles of imagery, professional geologists can identify previously unknown fault traces or confirm the activity of suspected ones at a speed and scale that would be otherwise impossible. This isn't busy work, it's genuine, impactful scientific contribution. A retiree in Florida or a high school student in Norway can now directly participate in mapping seismic hazards for communities on the other side of the world, fostering a profound sense of global citizenship and shared responsibility. This ethos of empowerment naturally extends into our schools and local communities, where the goal is to sow the seeds of curiosity that will grow into the next generation of Earth scientists. Educational programs are moving far beyond the baking soda and vinegar volcano model. Students might use simple seismometers built from everyday materials to record vibrations from the school bus driving by, learning the principles of wave propagation firsthand. They might participate in local field trips to observe road cuts that expose fault gouge or tilted sedimentary layers, seeing the evidence of tectonic forces right in their own hometown. The lessons are explicitly connected to daily life, how the geology of a fault zone influences the aquifer that provides their drinking water, or why certain building codes in their community require stricter reinforcement against lateral shaking. This approach answers the perennial student question: When will I ever use this? With immediate and compelling relevance, showing that geology isn't just about distant mountains and ancient time, it's about the safety of their home and the security of their water supply. All of this outreach, the documentaries, the apps, the classroom programs converges on a single, powerful outcome: resilience. A community that understands the geological hazards it faces is a community that is better prepared. When people understand the science, they are more likely to support funding for seismic retrofits of schools and hospitals, to have an emergency kit ready at home, and to know exactly what to do when the shaking starts. This demystification of complex topics replaces fear with knowledge and apathy with agency. It builds a culture of preparedness that is woven into the fabric of daily life, making societies not just harder to damage, but faster to recover. This collective empowerment, born from sharing knowledge openly and inviting participation, is perhaps our single most effective tool for mitigating the risks posed by the very forces that built the landscapes we call home. But with this incredible power to extract resources and knowledge from the earth comes a profound responsibility. The very act of studying and utilizing these fault zones forces us to confront difficult ethical questions. How do we balance our immediate need for minerals and energy with the long-term imperative to preserve these unique geological archives for future generations? A fault exposure that is obliterated by a mining operation is gone forever, along with all the unanswered questions it held. The environmental impact of such activities, from water contamination to habitat destruction, adds another layer of ethical complexity, reminding us that our pursuit of resources has real and lasting consequences for the ecosystems above these deep fractures. This is why the role of protected areas is so vital. Places like national parks and geological monuments act as sanctuaries for science. Think of the San Andreas Fault, gracefully exposed at the surface in places like the Carrizo Plain National Monument in California. This isn't just a tourist attraction, it is a world-class outdoor laboratory. Researchers from across the globe travel to such sites to conduct trenching studies, map subtle movements, and test new monitoring equipment. School children on field trips can literally place one hand on the Pacific Plate and the other on the North American Plate, gaining an intuitive understanding of tectonic forces that no textbook could ever provide. The careful management of these areas ensures that they remain pristine and accessible, not as frozen museums, but as living classrooms where the story of our planet continues to be read. This preservation is an investment in perpetual discovery, a guarantee that scientists 100 years from now will still have these fundamental references to turn to. Furthermore, the ethical framework for understanding these landscapes must extend beyond Western science to include the deep, time-tested knowledge of indigenous communities. For many Native American tribes, geological features are not inert objects of study. They are sacred places woven into their cultural identity and oral histories. Stories passed down through generations sometimes contain detailed accounts of landscapes changing, of earthquakes and volcanic eruptions that occurred centuries ago. These oral traditions can offer invaluable, long-term perspectives on geological activity that complement the shorter timeline of instrumental records. Collaborating with indigenous communities in a respectful and inclusive manner is therefore not just an ethical obligation, it enriches the scientific process itself. It fosters a more holistic understanding of the land, one that respects its cultural significance while unraveling its physical history. This partnership ensures that the pursuit of knowledge is conducted with humility and respect for those who have been its most attentive stewards for millennia. Navigating this complex terrain requires a constant, conscious effort to balance competing needs. A society needs the copper for renewable energy technology and the rare earth elements for our electronics, many of which are concentrated in fault-related deposits. But it also needs the untouched natural laboratories and the sacred spaces. The solution lies in a commitment to responsible exploration and the application of the most advanced, least invasive technologies available. This might mean using high-resolution satellite imagery to pinpoint mineral deposits with greater accuracy before any ground is broken, thus minimizing the footprint of exploration. It could involve directing mining operations away from the most scientifically critical fault exposures, even if it means leaving some resources in the ground. This ethical framework isn't about halting progress. It's about guiding it wisely, ensuring that the natural archives etched into our planet's crust remain intact to inform, inspire, and humble us long into the future. Looking ahead, the next frontier of fault research isn't just about better maps or more precise data. It's about sensing the Earth in ways we once thought were pure science fiction. We are on the verge of probing fault zones at depths that were previously unimaginable, thanks to a new generation of technologies that feel like they're pulled from a spy thriller. Take quantum gravity sensors, for instance. These aren't your ordinary instruments. They use the bizarre principles of quantum mechanics to detect infinitesimally tiny changes in the Earth's gravitational field. Why does that matter for faults? Because the density of rock changes around a fault zone cracks open, fluids migrate, stress builds. A quantum gravimeter, often housed in a backpack-sized unit, can be flown over a region like the San Andreas and essentially see these density variations in stunning detail, creating a three-dimensional image of the fault structure and its hidden fluid pathways from the air without ever drilling a single hole. It's like giving geologists a set of X-ray glasses for the entire planet, and for the places we absolutely must touch, there are projects of truly heroic scale. The International Continental Scientific Drilling Program, or ICP, is undertaking the geological equivalent of sending a probe to another planet, but straight down. Their ambitious projects involve drilling directly into active fault zones, like the Nankai Trough off the coast of Japan or the Alpine Fault in New Zealand, to retrieve pristine rock samples from the very heart where earthquakes are born. We're talking about drilling several miles into the crust, into an environment of extreme heat and pressure, to install observatories right on the fault. These borehole observatories are packed with seismometers, strain meters, and chemical sensors that will act like an intensive care unit for a fault, monitoring its vital signs, its temperature, its pressure, its faint whispers, in the critical years leading up to a major seismic event. The data streaming up from these depths will be a complete game-changer, providing a direct test of our theories about what finally triggers a rupture. This flood of new real-time data from satellites, drones, and deep boreholes is what will finally power the next leap in earthquake forecasting. The goal is to move from the broad probabilities of the past, like saying there's a 70% chance of a major quake in a region over the next 30 years, to something far more refined. Imagine a future where sophisticated computer models, supercharged by artificial intelligence, continuously assimilate live data from thousands of sources. These digital twins of fault systems would update themselves in real time, calculating how stress is evolving after a small tremor in one area or a change in groundwater levels from a heavy season of rain. While we may never predict the exact day and hour of a quake with 100% certainty, this integrated approach could allow us to narrow forecasts down to a window of weeks or even days, providing a level of warning that would fundamentally alter how societies prepare for and respond to seismic risk. But the quest to understand faults isn't confined to the classic earthquake country we already know. Some of the most groundbreaking discoveries are waiting in the planet's most extreme and inaccessible laboratories. Consider the fiery, volcanic rift valleys that snake along the mid-ocean ridges where tectonic plates are born. Here, faults operate in a completely different world, a pitch-black landscape of superheated water, bizarre mineral formations, and immense pressure. Studying these underwater fault systems with deep-diving submersibles could reveal entirely new mechanisms of rock deformation and mineral deposition, processes that might hold the key to understanding how life itself could have originated in such a chemosynthetic environment. Similarly, the immense ice sheets of Greenland and Antarctica present a fascinating puzzle. These miles-thick glaciers are themselves massive, slow-moving sheets of ice that fracture and fault. But more importantly, they press down on the continent below, hiding entire mountain ranges and fault systems we've never seen. Using ice-penetrating radar and hot water drills, scientists can now begin to map the subglacial geology, revealing how the interaction between a melting ice sheet and the rebounding crust beneath might influence the stability of hidden faults. This research is no longer just academic. It's critical for understanding how the rapid climate changes of today might indirectly awaken geological hazards we didn't even know were there. Every one of these advances, from the quantum to the glacial, promises to solve long-standing mysteries about how our planet works. But the most exciting outcome of all this research will be the new questions it inevitably uncovers. Each new layer of the Earth we peel back, each new environment we explore, reveals a deeper level of complexity we hadn't even anticipated. The journey of discovery is far from a straight path to a final answer. It's an endless, branching tree of knowledge where every answered question sprouts two new, even more fascinating ones. This relentless curiosity is what drives science forward, ensuring that our understanding of this dynamic, living planet we call home will never be complete, but will only grow richer and more profound with time. So as our journey through these deep cracks in the world draws to a close, let's take a moment to gather all the pieces of this incredible story we've uncovered together. We started by looking up at the majesty of a mountain range, but through the lens of science we learned to look deeper, to see these giants not as silent monuments, but as dynamic, living libraries. Their very existence is a testament to the titanic, slow-motion collisions of continental plates, a process that doesn't just build peaks but also shatters the crust, creating the deep faults that serve as our portals into the past. These fractures are far more than just scars. They are the planet's own filing system, meticulously preserving a record of events that unfolded over hundreds of millions of years, waiting for a curious eye to come along and learn how to read them. And what a story they tell! We've seen how the precise science of radiometric dating allows us to place absolute timestamps on these events, turning a chaotic jumble of rock into a coherent timeline of mountain building, continental rifting, and the assembly and breakup of long-vanished supercontinents. This chronological framework showed us that Earth's history is not a random series of events but a rhythmic cycle of creation and destruction. But the faults gave us more than just dates. They gave us a window into the very climate of the past. By studying the sediments and fossils uplifted and protected within these zones, we could reconstruct ancient worlds' lush carboniferous swamps that became our coal, vast deserts that left behind evaporite minerals, and oceans whose temperature we can still measure from the chemistry of a single fossilized shell. This archive provides the crucial long-term context for the rapid climate changes we see today, offering lessons from the past that are vital for predicting our future. The narrative became even richer when we discovered that these geological structures are also traps for the remains of ancient life. Faults, with their rapid burial and mineralizing fluids, have preserved exquisite fossils that offer unparalleled insights into evolution and biodiversity. This revealed a profound truth. The biological and geological histories of our planet are not separate threads, but are tightly woven together into a single tapestry. The rise of a mountain range can create new habitats and drive the evolution of new species, while a catastrophic asteroid impact recorded in faults worldwide can wipe the slate clean, setting the stage for a new evolutionary act. And let's not forget the immense practical value hidden within these cracks. The same fluid flow that lubricates faults and triggers quakes is also responsible for concentrating the world's great mineral wealth. The veins of gold, silver, and copper that have built empires and the structural traps that hold the oil and gas that power our modern civilization. This brings us to the most crucial point of all, application. This isn't just knowledge for its own sake. Every insight we've gathered from these deep faults directly translates into making our lives safer and our societies more resilient. The study of Paleoseismology, reading the evidence of past earthquakes in trench exposures, allows us to calculate the recurrence interval of major quakes, fundamentally rewriting hazard maps and informing building codes. Engineering marvels like base-isolated buildings and the fault-crossing Trans-Alaska Pipeline are direct applications of our understanding of fault mechanics, demonstrating how we can design our world to gracefully withstand the Earth's movements. And now, with advanced technologies like satellite-based InSAR and dense GPS networks, we are moving from historical analysis to real-time monitoring, edging closer to a future where early warning systems might provide those precious few seconds that save countless lives. Ultimately, the greatest revelation is that this work cannot be done in isolation. Deciphering Earth's secret past is the ultimate interdisciplinary endeavor. It requires the geologist mapping the outcrop, the geochemist analyzing isotopes, the geophysicist imaging structures deep beneath the surface, and the biologist studying extremophiles in deep fractures. It demands collaboration with engineers to build safely and with the public through citizen science and education to build a culture of preparedness. This collective effort underscores a beautiful truth: understanding our planet is a shared human journey. So the next time you stand before a mountain range or even feel a faint tremor under your feet, I hope you'll see it differently. You'll see a story still being written, a mystery still being unraveled, and a reminder that we are all living on a truly dynamic, ever-changing planet. We've journeyed together through the hidden world of deep faults, from the very foundations of mountain building to the cutting-edge technologies that now monitor their every whisper. We've seen how these geological features act as nature's own archivists, cracking open mountains to reveal Earth's deepest secrets, the epic cycles of supercontinents assembling and breaking apart, the traces of ancient climates and lost worlds, and even the fingerprints of catastrophic events that reshaped life itself. This exploration does more than just satisfy our curiosity. It fundamentally changes how we see the ground beneath our feet. It reminds us that our planet is not a static, finished product but a dynamic, ever-changing system, a work in progress written in stone and waiting for curious minds to decode its complex language. I hope this journey leaves you looking at the world with a new sense of wonder. The next time you're out on a hike, driving through a mountain pass, or even just seeing a photograph of a dramatic landscape, take a closer look. That mountain isn't just a rock, it's a history book. That valley isn't just an empty space, it's a chapter in the story of continental collision or rifting. Consider the immense forces, the unimaginable pressures, and the countless millennia that work together to sculpt that view. This perspective connects us to a timeline far grander than our own, offering a humbling and powerful sense of our place on this active planet. The conversation doesn't have to end here. I'm truly curious to hear what you thought about this deep dive into Earth's mysteries. Did any part of this story surprise you? Do you have a favorite geological wonder you've visited? Share your thoughts, your questions, or your own experiences in the comments below. Let's keep the exploration going together. If you enjoyed unraveling these secrets with me, please show your support by giving this video a like. It really helps the channel grow. Make sure to subscribe and hit that bell icon so you won't miss our next adventure into the fascinating stories of our world and beyond. Thank you so much for watching, for your curiosity, and for your time. Keep looking down, keep asking questions, and never stop exploring the incredible wonders hidden right beneath our feet.